Welcome to the fifth installment of Math 3350 Online Probability and Statistics. Today we're not going to be learning new material, we are going to put old material together in a slightly different context. Okay, so our probability formula is the number of outcomes in the event set A divided by the total number of outcomes possible. So now we're going to use the counting patterns that we've discussed in the previous two sections, in sections 2 and 3. And we're going to see if we can solve probability questions where we do a counting problem in both the numerator and the denominator. So for example, what is the probability that a random arrangement of the 10 letters aftershock results in the first 4 letters that we draw out spelling the word safe? Here's the situation. We have the 10 letters aftershock, and they're going to be permuted, right? This is a permutation, and if we rearrange the letters into some permutation, we're going to have 10 slots, which you can see numbered there. And then the question is, how many of these slots, how many of these rearrangements will have the word safe spelled out in the first 4 slots? Well, there's only one way to have an S, an A, an F, and an E in the first 4 slots. But then there are 6 choices left for the 5th number and 5 choices left, and then 4, 3, 2, and 1 choice left for each of the other numbers. So that means there are 6 factorial ways that the word safe could appear in the first 4 letters, and then the remaining 6 letters are permuted. Okay, so what's the probability? The probability that they're asking for, the probability that the word safe is spelled in the first 4 digits, right, is the 6 factorial over 10 factorial. So we need to get used to dealing with these permutations where some restrictions are made. So here's a second example. What if we have the 9 letters in the word amplitude and we rearrange them? What's the probability that the first letter will be a P and the last letter will be an M? So here's the situation with 9 letters. Again, you can just set up the restrictions, right? Put P in the first slot and M in the last slot. There's just exactly one way to do that. The question is, how many ways are there to rearrange the following letters? And so we're looking at all the different rearrangements of 7 different letters into 7 slots. So 7 factorial. So this probability is going to be 7 factorial over 9 factorial, which is 1 over 9 times 8. Sorry, 1 over 9. 1 over 9 times 8, which equals 1/72. Okay, notice that this is also the probability I get when I take, and I say, hey, well, what's the probability of drawing drawing a P into some slot, right? Well, there are 9 different letters, so that probability would be 1/9. And then I can use conditional probability, and I can say, well, if I've already drawn a P into a specific slot, what is the probability that I draw an M into another specific spot, given that a P has already been drawn? Well, that's 1/8. And so you can see, that's why I broke this up in this denominator right here. So either approach works. We can use, the first way used a counting method, and then the second way used conditional probability. Either approach is fine, but you should be able to do both. So the game of spades is played with all the cards dealt to 4 players, so each player gets 13 cards. And spades are valuable because they're always the trump suit. So they're asked the question, what is the probability that each player, that Shiro, our Shiro here, gets dealt a hand with exactly 10 spades? Or we have a second question, what is the probability she gets dealt a hand with 10 or more spades? So if we let this set S sub 10 represent drawing exactly 10 spades into a 13 card hand, then we can use the partitions to solve this. So the probability the probability that S10 occurs. Well, let's do the denominator first. The first piece of this is these are combinations, right? Order doesn't matter. It doesn't matter in which order you get the spades as long as you get exactly 10 of them. So the total number of possible ways to draw 13 cards from 52 is 52 choose 13. Okay. Then we can use the ready-made partition in the deck of cards because we have 13 spades. So from those 13, we're going to choose 10 of them. But we have to choose the remaining 3 cards. Well, the remaining 3 cards can't be spades because we have to have exactly 10 of those. So from the remaining 39 cards, we're going to pick the remaining 3 to go into our hand. So that's the probability of drawing exactly 10 cards that are spades. I haven't yet done any videos about how to use your graphing calculator. I do suggest a TI graphing calculator for this course, and here's why. So if I want to evaluate this probability here, right, I need to do 13, choose 10. So I type in 13, and then I go to Math, and I arrow over to the probability menu, and option number 3 is the combinations, NCR. So I do 13 choose 10 times 39 choose 3. And it's like there's imaginary parentheses around this whole thing. It's not going to multiply the 10 times the 39. It's going to do the 13 choose 10 times the 39 choose 3. And then I can divide this by 52 choose 13. And so you can see this extremely big number, which is our probability. But the question asks us, what is the probability? They also ask not just the probability of exactly 10 spades, but 10 or more. And what do we do here? So this probability is not any harder. It just requires us to do several more of these counting problems, right? So the next one we need to do is the probability of S11. Probability of S11 is going to have the same pattern. It's going to have the 13 choose 11 times the 39 choose 2 over 52 choose 13. And we're also going to have the probability of S12, which is going to be equal to 13 choose 12 times 39 choose 1 over 52 choose 13. And finally, we're going to have the probability of S13, which is going to equal 13 choose 13, which is, by the way, is 1. There's just one way to choose all 13 spades into a 13 card hand over 52 choose 13. So to get the answer to this question, we would have to add them all up. We'd have to take the probability of S10 plus the probability of S11 plus the probability of S12 plus the probability of S13. But I'll leave the calculations to you. Our next example is permutations around this conference table. So permutations on a circle. And we have 12 students in the class that are going to be seated around this seminar conference table. And we have 2 students who are secretly dating, and what is the probability that Terrell and Jade end up seated next to each other if the seating chart is put at random, and also it's just the 12 students, the professor isn't there at the table with them. Okay, so we want to calculate the probability that the J and the T are together. I'm thinking of this as 12 letters permuted around a circle, and I want the J and T to be together, but that means that it could either be JT or TJ. There are two ways that they could be seated next to each other. And we're doing a permutation on a circle, so there are, as we learned in section 3, there are 11 factorial ways to seat 12 people around a table, 12 different, 11 factorial arrangements, 12 minus 1 quantity factorial. Okay, and there are just so then how many of these are we'll put these two together? Well, think of it this way: we'll think of J and T as a single unit, and then there are 10 other students. So now if we think of J and T together, right, think of them as a couple. We have a couple and 10 other students. So we have 11 items to permute around the table, which is 10 factorial, right? Because it's 11 things permuted on a circle. So we have 10 factorial, right? So the answer here is going to be the 10 factorial permutations, and then we have J and T or T and J. So this is 10 factorial times 2. So this turns out to be 2/11ths. All right, which makes sense because you could also think of what if Jade was seated first, right? Then there's the seat on her left and the seat on her right. So there are 2 seats that her secret boyfriend could be seated at. So either way, whether we think of this as placing one person and then checking the probability to see what the chance is the other person gets seated next to them, or if we do that as a counting problem like we started with, either way we get the same answer. The final question we're going to look at is a Cartesian product. What is the probability of rolling 3 fair 6-sided die and getting 3 5s? Well, we have a Cartesian product, right? We have a dice roll which has 6 outcomes, right? Cross, taking the Cartesian product with another dice roll of 6 outcomes, crossed with another dice roll, right? So there are 6 times 6 times 6. There are 6 cubed outcomes. And then the question is, what is the probability of rolling 3 fair-sided dice and getting 3 5s? Well, there's only one way to get a 5 in each of these slots. So the probability is equal to 1 over 6 cubed. I do want to point out that it's not always the best way to use counting techniques, but it's often the best way. So I showed one example where we could calculate conditional probabilities instead of doing the counting problem. Actually, I showed a couple like that. So it's good to be flexible. You do need to know how to use both ways if you're going to be successful. But on any given problem, you can use whichever method you prefer, whichever makes the most sense to you. It's always helpful to be able to use a second method to double check your answer. Be sure to do the completion quiz for Module 5. Good luck.